Hello, my lovely Algebra 2 students. This is Mr. Bear, and we are going to start off this semester with some probability information. So in class, you're going to start off with an activity where you're going to do a game where you and a partner are going to toss a die. Because I don't have the ability to do this in the notes here, what I'm going to do is I am just going to get right to the. Let's see. I mean, I would love to do this with you all, but I just don't want to waste the time to do that on here. So, this part right here will be something that you're going to do in class. The idea is that you and a partner would be rolling a die. And what you're going to do is one of you will be player one and the other will be player two. You roll the die, and if a number 1 through 4 comes up, player 1 wins. And if a number 5 or 6 comes up, player 2 wins. And you'll want to kind of ask yourself who has the advantage, player 1, player 2, or neither. So you'd want to kind of make your best guess. And then you would actually take turns rolling your die and tally up who wins each of these trials, which would be each time you roll the die, that's considered a trial. And then calculate the percentage of wins. And then what you want to do is figure out how many times the player 1 win and how many times the player 2 win. And then what we would do is we would gather the data from each person and we would end up creating a class set of data. So what I want to do is talk about how to determine the true probability of player one winning. So what we're going to do is we're going to create what's called a sample space. Okay, this chart right here is going to give us what's called a sample space. And it's going to tell us all the possible outcomes of what would happen if we look at each person rolling the die. Okay? So the 1 through 6 going down here is going to represent player 1's die. So player 1. Or I guess it doesn't really matter which player, but in this case we'll call it player 1. And this 1 through 6 up here is going to represent the player 2 person. And 1 comma 1 means player 1 rolls a 1 and player 2 rolls a 1. So this next box here would be 1 comma 2. So player 1 rolled a 1, player 2 rolled a 2. And then we'd have 1 3, 1 4, 1 5, 1 6. And then we would go and continue filling this in. And you kind of see where this is going to go. So I'm going to pause this video to fill in the rest of this. And now we can see all the possible outcomes. Okay? So now what we want to do is we want to use the table to find out the probability of player 1 winning. Well, player 1 wins, if we go back up to the scenario here, player 1 wins if the largest value shown is a 1, 2, 3, or a 4. Okay? So what I'm going to do let's use the highlighter tool. Oh no, let me just I'll circle them in gold. How about that? So I'm going to circle all the ones where the highest of the ones rolled is a 1, 2, 3, or 4. So these are definitely going to work. These are going to work. Whoops, I missed one on that. Eek. Also accidentally erased a number. Let me go back and put that number in there. Oops. Okay, so all of those are examples of where the highest value is a 1, 2, 3, or 4, which means the player 1 would win. Okay, so looking at that, that would be, so we have to first know how many total little squares are there inside of this big box. So it's 6 by 6, so we know there's 36 total possible outcomes, and we circled 16 of them. So the probability of player 1 winning is 16 out of 36, which if we simplified that down, we could divide those by 4, so that would be 4/9, or about 44%. Okay, and so based on how that compares to what we did in number 2 here, that will tie into a concept that we'll talk about on the reverse side of these notes. But anyway, so what we did here was we talked about this here is what we call theoretical probability. Okay. Theoretical. Theoretical meaning that that's what we expect to happen based on just knowing that there are 36 outcomes, and 16 out of the 36 we expect will be a dice that will roll of 1 through 4. Okay? Now, when you and your partner actually roll the dice and came up with your stuff, this up here is what we would call experimental. And you calculate experimental probability by figuring out how many times something occurred when you did it, divided by the total of number of times that you actually perform the experiment. Okay, and we'll define these on the next page. Okay, so let's talk about some probability models and rules. So these are the important ideas. Okay, so this is the stuff you need to make sure you're writing down. So when we talk about long run frequency, short term frequency, by the way, is unpredictable or unreliable. Long term frequency is a little more predictable. Okay. These next two ideas are going to be what I was just explaining a moment ago. So theoretical probability is what we expect to happen. And that's where you take your favorable outcomes divided by your total outcomes. So like for example, if I flip a coin, we know that there are heads and there are tails. So that means there's 2 total outcomes. If I want to know the probability that it's going to land on tails, tails is 1 out of the 2 outcomes. So we would say the probability is 1 out of 2. If you're rolling a number cube or a number dice, there are 6 sides to that. So the total possibilities are there are 6. Each of the numbers on the number cube would represent 1 out of 6. So you would have 1 out of 6 for each of the numbers. So to roll a 1 would be 1 out of 6. To get a 2, it'd be 1 out of 6 because there's one side that has a 2 on it, etc., etc. Versus experimental probability, which is a little bit different. The main difference between theoretical and experimental is that for an experiment, think about an experiment, you have to actually do something. So experimental probability is what actually happens. So it's outcomes over trials. So a way to think about that is, let's say you're actually flipping the coin and you want to see the probability, the experimental probability that your coin will land on tails. Let's say you flip the coin 20 times and it lands on tails 15 times for whatever reason. Your experimental probability of getting tails is 15 out of 20. That doesn't always have to match the theoretical probability, especially if you don't do it very many times. 20 times, not a very long-term frequency, so it's not very predictable. But that would be your experimental probability because that's what happened in your experiment. Okay? All right, so now let's define what probability is. So this right here is notation for probability of event A. Okay, so when you see this notation P parentheses event A, P stands for probability. So this is just saying probability of event A just means something occurring. We're just calling it event A. So the way we'd say that is we define it as number of times event A occurs divided by total outcomes. Okay, so this means probability of event A occurring. Okay, so you should already know this idea. So to find the probability of something, you see how many times the event occurs divided by the total number of possible outcomes. Now the next word here is another vocab word, complement of an event. When you see the word complement, basically it is so if you have an event A, the complement of event A is what isn't event A. So like let's say that I'm rolling a number cube and let's say event A is rolling a 1. The complement of rolling a 1 would be not rolling a 1. So it'd be getting anything except a 1. Or if event A is defined as rolling an odd number, well, what's not an odd number? Well, it'd be an even number. So the complement of an odd number would be an even number. So basically what's not the event that you're looking at. So the complement is everything outside of the event that you're looking at. So the way to think of that is whatever event A is, the complement of it is, you would say, the probability of not whatever the event A is. And you define that, let me use a different color here. We do that as 1 minus the probability of event A occurring. Okay? So to find the probability of a complement, you just take 1 minus whatever the probability of event A is. Okay? For the probability of A or B, you take the probability of event A, add it to the probability of event B occurring, and that's if A and B cannot occur together, cannot happen together. Meaning that you can't have something that is both A and B. So like for instance, if A is an even number and B is a multiple of 3, that would not be a situation where you could do this because we would have multiples of 3 that could also be even numbers. Okay, so keep in mind that if you're trying to find a probability with the word or, you can only add them together if A and B are what we call mutually exclusive. Okay, so that's the fancy way to say this. And we will talk about that in a future lesson. But for now, just know that if you have the word or, we're going to be adding probabilities together. To find the probability of at least one of something happening will be 1 minus the probability of none. Okay? So if I wanted to find the probability of at least one, I can't think of a good example right now. Probability of at least one something being drawn from a hat, I could take 1 minus the probability that none is drawn. That would be the quicker way, because basically that is the complement of at least 1. All right, so for probability models, the way that we're going to do probability models is first we're going to list all the possible outcomes. Again, that's what we call the sample space. Note that all probabilities are between 0 and 1, where 0 probability is it cannot happen. So that would be impossible. And a probability of 1 is certain to happen. And every other probability is going to fall somewhere in between those extremes. And note that all probabilities must add up to 1. So if you have a list of different probabilities, they must all add up to 1. So if you're looking at a list of a bunch of different probabilities related together in your sample space, they must add up to 1, because in order for a sample space to contain all the possible outcomes, that means that everything in that sample space at some point is certain to happen. So you would have to have all the probabilities add up to 1 to be sure that all the possibilities do in fact happen. All right, so let's do some practice problems here real quick. So let's start with some Skittles here. So we have a list of the colors of Skittles and some probabilities. So first, let's explain the probability of 0.214 for purple. What does this mean? Well, it means that approximately 21.4% of all Skittles are purple. Okay? Or 21.4, a little over 21 out of every 100 Skittles will be purple. Okay? What is the probability that a Skittle will be red? Well, we aren't told red, but since these are the sample space, this is the sample space, these are the only colors, of Skittles. And we're talking about just the traditional ones. There might be like the weird, I shouldn't say weird, but there might be the different flavor types of Skittles, like, you know, the tropical ones or the whatever. These are just traditional Skittles, okay? But when you look at these Skittles, these are the only possible colors of Skittles, so these probabilities have to add to 1. And since they have to add to 1, we're going to do 1 minus the sum of the other colors. Okay, and so what I'm going to do is I'm going to take my calculator just real quick, and I'm going to add up the ones that I know. And I get 0.197. So it looks like the probability of red is a little under 20%, so 0.197. What's the probability that a randomly selected Skittle is green or purple? Since a Skittle cannot be both green and purple, so that means that you can't have a green Skittle also be a purple Skittle, we can just do this as probability of green plus probability of purple. Probability of green is 0.171. Probability of purple is 0.214. We're going to add those together. So again, I'm just going to go to my calculator. And we get 0.385. So about 38.5% of all the Skittles are green and purple. So if those are your favorite colors of the Skittles or your favorite flavors, then good. Over a third of the bag is made up of those. What is the probability that a randomly selected Skittle is not yellow? So to figure out not yellow, you do 1 minus the probability that it is yellow. So that'll be 1 minus, let's see, yellow is 0.214. So we're going to go to our calculator and do 1 minus 0.214, and we get 0.786. So if you aren't a fan of the yellow ones, the good news is almost 79% of the bag is not yellow. So take those 79%, enjoy those, and then give the other 22-ish% to your friend. All right, that is what you need to know about probability. Have a great day.